Hello and welcome back to Let's Code Physics. I've done a little bit of work off camera to our Pendulum code to add in a Poincare map. If you need a refresher on that, I'll include a link in the description below to when we first used a Poincare map back in, I guess that was season 1, so last fall, when we were doing the gravity simulator. You might remember last time we started looking at the phase space plot of our double pendulum, and that screen was getting pretty crowded pretty quickly, and that's because it's showing every single data point for 2 of the 4 parameters that describe each double pendulum. So each double pendulum is described by an angle and by that angle's time derivative. So when you've got a double pendulum, you've got a theta for the top one, a theta for the bottom one, and a theta time derivative or an angular speed for the top one, and then an angular speed for the bottom one. And we want to be able to compare multiple pendulums at once because we're starting out with slightly different initial conditions. So they all start at rest, so it's like somebody's releasing them from rest. But for the second one, the one that's been shown in white, the bottom angle is up by 0.1 pi radians compared with the green one, the first one. And we saw that it produced some differences, but it's kind of hard to tell those differences when the phase space plot gets so crowded. So we're trading that out today for a Poincare plot. The way a Poincare plot, or I think it's more properly called a Poincare map, because map sounds fancier than plot. The way a Poincare map works is you're still showing 2 of the values. So for example, for the green pendulum, how about I put a note up there that this is the green pendulum. So for the green pendulum, we're showing its top theta versus its bottom theta. Same thing for the white pendulum. It's the bottom theta versus the top theta. If I wanted to do more, I could just add more graphs. So if I wanted a plum pendulum, I could add a plum pendulum. If I wanted a scarlet pendulum, I could add a scarlet pendulum. Basically, that's going to show those 2 versus each other, but it's only going to graph one dot at a time. So instead of doing a G curve like we had last time, it's now a G dot. So it'll add one unconnected dot at a time. And so what we have to specify are special values of the theta dots, right? So so we're only graphing the theta 1 and the theta 2, which means that the dots are left off of the graph. So what we're doing is we're only adding a data point whenever theta 1 dot and theta 2 dot, or the upper theta and the lower theta, are equal to some special value. It made sense to me to make those values equal to 0, both because it would be interesting to see at what points the whole system these are equal to 0. Then the double pendulum system is momentarily at rest, and also because that's our initial conditions for theta 1 dot and theta 2 dot. And it just occurs to me it shouldn't make a difference, but let me add some point zeros on here. I was working with a student just yesterday, and they were getting some weird results, and it was because they hadn't put a 0.0 on, and it was doing integer division instead of floating point division. Of course, these are zeros. We shouldn't be dividing by them anyway, but just in case. So basically, it's only going to create a plot on the Poincare map, or point on the Poincare map, when both of these things are equal to 0, to the specified or special value. That's what the spec there stands for. So we'll label that as specified value of theta 1 dot. And then it's just sort of et cetera down here. I've commented out all of the other visuals in order to improve the code's runtime. So there's not going to be an animation anymore. It's not even going to be the phase-based animation anymore. It's just going to create the 2 separate Poincare maps. I've maxed out the rate. I haven't. If I take this out, it'll definitely max it out, but then I won't be able to see it evolve as it goes. And so I want to be able to cut the program whenever it whenever it seems to have gotten a nice shape to it, which I haven't figured out how to tell the code to look for a nice shape yet. And if I had my webcam on, you'd see my finger quotations when I say a nice shape. And so it's going through the same calculations as before. It's just getting rid of everything having to do with Bob and Rod. Sorry, Bob and Rod, you were not invited to this dinner party. How many more clue jokes can I make in this episode? I'm not adding any ones and twos. That's too bad. And so here is where it's creating the dot. And basically it goes through this long process to see whether theta 1 dot and theta 2 dot have passed through their special values. And so it's keeping track of what the current value of each one is and what the last value of each one is. So at the end of each loop, it's updating the last value with the value that was just calculated. And so it's saying, is the current value greater than the special value and the last value less than the special value? Or is the reverse true? Is the current value less than the special value and the last value greater than the special value, meaning that theta 1 dot passed through the special value? And then this line is the same thing for theta 2 dot. And then these lines are the same thing for theta 3 dot and theta 4 dot. And so it's only graphing when theta 1 dot has passed through its special value and theta 2 dot has passed through its special value. And it's only graphing here if theta 3 dot and theta 4 dot have both passed through their special values. And this happens surprisingly more often than I would have thought. I originally just had the theta 1 dot and the theta 3 dot, and I was letting the lower angles just kind of swing free, so to speak. That was a pun, so that was in the spirit of Clue, at least. But that made the graph too full. And so surprisingly, you put this in and it still creates or it still creates a pretty noticeable pattern. And so what I'm going to do is I'm going to run this a few times over probably the next week here and there, because it takes about an hour and a half for each one to come up. I'm not going to video record it. I've learned not to do that because sometimes the video card crashes, sometimes my computer needs to restart, and that doesn't work, and that's not as interesting to y'all. So what I'm going to do is I'm going to run this several times with different values of length. So right now the penduli, whatever they are, each pendulum is identical to the other. They've got the same mass and they have the same length. Actually, this one I just recently changed to 50% of this one. So we started out with them having the same mass and same length. I've actually already run the scenario for equal lengths. And what I'm going to do is I'm just going to grab the graphs as a screenshot. And then after I'm done with that, I'll come back to the recording studio, aka this corner of the front bedroom in my wife's house, and then I'll just go over those results, and we'll talk about them. We'll talk about how they change as the length changes, and we'll talk about them how they change as the mass changes. I think I'll need to change both the length and the mass independently, because they don't always occur in the same proportion. So like, for example, that's the energy one. Because the length and the mass, they mix differently. So like you've got M total times length 1, you've got mass 2 times length 2, but then you've got mass total just multiplying the gravitational constant. So I suppose I could also vary the gravitational constant. It would be a fun thing to do. So anyway, I'm going to work on that over the next several days, and I will see you after the break. Well, it has been a couple weeks since I recorded that introduction. It turns out this takes quite a while to run, especially for the lengths that are very, very different. This initial one that I set up for you, the length 2 equal to length 1. So again, length 2 is the bottom pendulum rod, length 1 is the top pendulum rod. This one ran in, I think, about like 2 or 3 hours or something, and I was able to get this nice graph. But the farther away I got from length 2 equal to length 1, the code took much, much longer to run, meaning it took longer to get this same number of data points on the screen, or the same saturation of data points. And so that tells me that that these points happen a lot less frequently for very unequal lengths compared to mostly equal lengths. That also might be because I had other stuff running in the background, like Unity, Chrome, YouTube, things like that. So, I also was probably putting some extra strain on my computer, but I had to have it run like for an entire day for the most recent couple of ones. Anyway, enough computer woes, on to the physics. So, thank you, Java. I said enough computer woes, enough. So, one of the things I learned is that the initial conditions, so you remember we were running two pendulums at the same time, one with a slightly different initial angle than the other. It turns out that didn't make too huge a difference, so I'm only going to present the first one, whatever that initial condition was. It didn't really make a huge difference in terms of the map. Like, these might have shifted over a tiny bit, but the general shape was still the same. And because this is taking so long and I want to update you on it, I'm only going to talk about the changes in length today. After I'm done recording this discussion, I will go back and start varying the masses. And so then we'll see what the effect is of the masses, because for a regular pendulum, changing the mass and changing the length doesn't do all well. Actually, I guess the mass completely drops out of the simple pendulum. But normally things like that are interchangeable. But there's some terms that have different combinations of L's and M's. So anyway, this is for the two pendulum lengths being equal. And so you get this interesting shape. So again, this is a Poincare map, meaning these are the values of the angle of the bottom rod versus the angle of the top rod whenever their velocities are both equal to 0. So these are the points at which the pendulum was observed to come to rest, where the, there we go. So these are the points where that was not at rest. These are the points where the pendulum was observed to be at rest, both the top rod and the bottom rod. So you can see there's some scattering of points in these corners, but then there's this nice little pattern here. So there's these two, I think you call those attractors in this nomenclature, where basically the points tend to cluster. So you've got this little swoosh of a line here. You've got this little swoosh of a line here. And there's a nice little vertical symmetry to it, because basically at pi over 2, so at 1.5-ish over here, the system is symmetric, right? Because the system is left-right symmetric. And so you'd expect it to be more or less mirrored, and that's what you get. So these two little swooshes, they overlap some. So there's this region in the middle here where they never go. So it seems like the pendulum seems to never come to rest in this configuration of angles. So you can think of that as kind of being a picture of conservation of energy, I suppose, where this combination of potential energies doesn't satisfy the total amount of energy of the system. There is also a dearth of points up here, and not quite so much down here. So I might expect, if you ran this longer, to get more of a scattering of points up here. Yes, thank you so much. So if we go to the next one, this is where the bottom rod is 50% longer than the top rod. You get more or less the same shape. For whatever reason, there were fewer scattered points in this region. I might not have run the code for as long, but you get the same general shape between these two swooshes. And my scales are not quite perfect because the G-curve did an auto scale. I didn't set the maximum, but they're basically all going from 0 to pi. It's just a slight difference. But you notice that these are starting to curve a little bit differently. You especially start to notice it when you go up to length 2 being twice as long as length 1. So these swooshes they're starting to creep outward a little bit. Same thing with the 2.5. That curvature is starting to go away here. And so this region here is starting to get a little bit bigger, where you don't have any points. And so these are kind of starting to uncurl. So if I go back up, you see the curves here, they're starting to curve inward a little bit more. Here they're curving all right. Here the point of curvature, if you wanted to find a corner for it, is starting to push out a little bit. This one, it's hardly turning down at all. It's not turning up very much. If you go to L2 equals 3 times L1, these things are nearly straight. I mean, the curvature is starting to get almost unnoticeable. Oh, and that is as far as I went, was 3, because after that it seemed to be keeping the same behavior. So if I flip back, you can see the curvature evolve, which is kind of cool. Of course, that's not the only situation we want to look at. We can also make L2 shorter than L1. So here L2 is 3/4 the length of L1. So this is one of the ones I had to have run for like a day or 12 hours or 18 hours or something. My computer was putting in some overtime. And so there were a lot more, sort of random points around here in order to get the curvature. So if you notice, there's definitely a difference, because the curved line here is going out to about 1, going out to about 2 and some change. Oops, wrong way, Ryan. This one, it's stopping well short of 1, stopping well short of 2. If I go to half the size, there's this huge break. So the difference between 3/4 the size, so 75% of the size, these are still overlapping, and half the size, there is this huge break in between there. Now, if I let this run for longer, there might be more points there, but again, this thing ran for, this one might have run for like 36 hours or something. I mean, I just stopped it yesterday because I had to go to class, and I was like, all right, I got to record this tomorrow, because this is taking forever. People are wondering what's happening with the Poincare maps. Of course, for y'all, it's just been like a week because I recorded all those ahead of time. So yeah, this gives you an idea of some of the neat stuff that you can observe. So it's kind of interesting how this, this overlap gets broken because of the difference in the pendulum lengths. So the next thing I'm going to do is play around with the pendulum masses and see what kind of variation we get. I expect we'll get kind of a similar shape change, but I do not know. So I will take a look at that, and we'll examine it together. So thank you so much for watching. I will see you next time. Bye-bye. Format background, give me a solid fill. I see a background and I want to paint it black. Apply to all the backgrounds, I want them to turn black. There is a yellow line around those little windows, but that's okay, they'll be there until this video is posted.